What if we could take an impossibly complex, chaotic mathematical function and entirely replace it with a simple, predictable algebraic expression? In applied physics, machine learning, and computer science, processing arbitrary functions like sine waves or exponential curves is computationally expensive. It slows systems down. Taylor's theorem provides a mathematical bridge for this problem, converting those difficult continuous curves into highly efficient polynomial equations. But to build that bridge, we have to meet strict criteria. On page 110 of Rudin's Principles of Mathematical Analysis, we see the prerequisites. Derivatives up to the n-1 degree must be continuous, and the nth derivative must exist on our interval. Mastering this theorem establishes the mathematical framework required to process complex physical simulations and large-scale data with predictable accuracy. The logic underneath Taylor's theorem begins with something much simpler, the standard mean value theorem. You can think of it as the foundational n=1 case. This animation shows the geometric reality of that first-degree case. We approximate a curve by starting at point alpha and extending a straight tangent line. The BAP between that straight line and the curve is our error, depending entirely on the first derivative, its slope. So what happens if we don't just use the first derivative? What if we use every known derivative at point alpha, all the way up to n-1? Adding the second derivative corrects for the curve's concavity. Adding the third derivative corrects for the twist or torsion. With each added term, we physically bend that straight line into a complex polynomial that tightly hugs the original curve around our starting point. Rudin formalizes this exact curve-hugging intuition into a rigorous algebraic proof. Taylor's theorem isn't a new concept. It is the mean value theorem scaled up to n degrees, systematically crushing the approximation error with every step. On page 110, Rudin lays out Theorem 5.15 and defines our polynomial in equation 23. By centering the summation on alpha, we guarantee the polynomial's value and its n-1 derivatives exactly match our original function at that point. But no matter how perfectly we match the function at alpha, when we travel to evaluate it at a distant point beta, our polynomial is still just an approximation. In equation 24, Rudin quantifies the remainder. It relies on the nth derivative evaluated at an unknown point x divided by a factorial and multiplied by the distance between alpha and beta to the nth power. That existence alone sets a rigid error bound. In strict mathematical analysis, constructing the matching polynomial is trivial. The true genius lies in isolating, bounding, and strictly defining the error it leaves behind. To prove this, Rudin defines m in equation 25 to represent that missing gap at beta. He then builds an auxiliary function, g of t, representing the original function minus our polynomial, minus the scaled error term. This sets up two critical boundary conditions. First, because of how perfectly we built the polynomial at alpha, g of alpha equals 0, and all its derivatives up to n-1 also equal 0. Second, because we forced m to represent the exact gap at beta, g of beta must evaluate to 0. We can visualize this on a timeline, tracking the roots of g of t. Because g is 0 at alpha and beta, the mean value theorem dictates its first derivative equals 0 at an intermediate point, x sub 1. But our first derivative is also 0 back at alpha, giving us a new pair of roots. This triggers a cascade. The second derivative must be 0 at a new intermediate point, x sub 2. This logical trap repeats n times, with each successive derivative, the interval shrinking until we guarantee a final point, x, where the nth derivative of g is exactly 0. Let's pivot back to equation 27 to see the nth derivative. Because our polynomial has a degree of n-1, differentiating it n times reduces it to 0. The only surviving algebra is the nth derivative minus n factorial times m, which equals 0. Solving for m by dividing by n factorial perfectly recreates the exact remainder term Rudin proposed, completing the proof. By constructing a custom error function that zeroes out at its boundaries, Rudin forces the mean value theorem to cascade down and expose the error. Stepping away from the algebra, what does this remainder term actually look like in physical space? In this visual, we see the true function and our polynomial approximation. The remainder term defines the literal vertical gap between them at a distant point, beta. If we can determine the maximum possible value of the nth derivative across our interval, we can calculate a worst-case scenario for that gap, generating a shaded error envelope around our polynomial. Even if we don't know the exact value of the original function at a specific point, we have mathematically proven it must exist within this strict boundary. And because n factorial sits in the denominator of the remainder, as we add more derivatives, that factorial grows astronomically, crushing the error envelope tighter and tighter against the approximation. Knowing local behavior at a single point dictates the function's global behavior, bounded only by the strictly defined, ever-shrinking error zone. This theorem is the engine of modern computation. When computers process transcendental values, like the sign of 0.1 or natural logarithms, they execute Taylor polynomials. In physics and engineering, nonlinear differential equations are modeled by utilizing this exact remainder term to guarantee the precision and stability of a simulation. It makes continuous mathematics computationally accessible by safely replacing the infinite with the finite. The rigor found in proofs like Rudin's provides the theoretical guarantee needed to trust that our simulations will remain within their calculated margins of error. With enough derivatives, the complex becomes simple. If you want to continue exploring the rigorous foundations of higher mathematics, subscribe for our next deep dive.